walk in the room, find me where she went, I would follow. Walking through the land of tomorrow, Martian trinkets, plastic Apollos. Hello, and welcome back. Well, this is the 7th video, officially named 7th video. I think it's the 8th. Or 9th, because I messed up a previous video somewhere. So today I want to wrap up quantum mechanics as a system of thought and move on to special relativity, because in special relativity I'll be able to demonstrate the luminocentric principle, and that's the real reason why I'm doing this series. I want to demonstrate the luminocentric principle, which I so name because because it reminds me of the heliocentric principle. You know, the planets rotate around the sun instead of the sun rotating around the planets. Well, it turns out that light is the center of the universe, not matter. Matter is in motion, light is not. That's the luminocentric principle right there, and I'll be able to demonstrate it, believe it or not. So I want to wrap up quantum mechanics. Let's start with the story of 2 rabbits and 2 proteins. I don't want to wrap up the subject of quantum mechanics as if it had nowhere to go. I just want to change the subject to special relativity, that's all. Now, let's begin by modeling the growth of 2 proteins, protein A and protein B. The assumption here is that protein A requires the presence of protein B and some raw materials to make copies of itself. And protein B requires the presence of protein A and some raw materials to make copies of itself. So we begin by writing the differential equations, dA dt, the rate of change of growth in A with respect to time, equals the function bt, the b of t, the amount of protein B, and the rate of change of growth in the amount of protein B with respect to time equals A of t. I'm not going to bore you with the system, with the details, with which you certainly have seen somewhere before, or maybe not, but you will. Who knows? So the solution goes A of t equals B of t equals e raised to the t, the natural exponential function. And the assumption here is that at t equals 0, A of t equals B of t equals E of 0 equals 1. So they're both starting out from 1. Now, to model the population of 2 rabbits, rabbit A and rabbit B, again, I'm assuming you all know this, it's the Fibonacci sequence. And I just want to show some pseudocode for the rabbits. Okay, so while true, okay, I'm calling these rabbits little a and little b. The amount of little a is incremented by the amount of b, right, itself, plus b, and the amount of b gets incremented by itself plus the amount of a. And then we print little a, we print little b, and chana, out comes the Fibonacci sequence. Why am I saying this? Because if we do a little adjustment here, if we if instead of incrementing a, well, we initialize the counter to 0, and then instead of incrementing a by b, we're incrementing a by b times a little fraction, like let's say t equals 1 over 1,000. And we're doing the same for b. And then we're updating this counter, and then we have some kind of test to see if the counter has reached a multiple of 1 over t. For example, we can start by printing out the values of a and b, but that's trivial because they would both come out to 1. And then on the thousandth iteration of the loop, we print the values of a and b. And then on the 2000th run, and then on the 3000th run, the 4000th run, etc., we're printing out the values of a and b. And what's going to get printed is approximately this. Well, first we get 1 and 1, and then we're going to get like 2.71 blah 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 for 1, and then we're going to have 2.71 blah. Well, approximately e is going to come out at step 1000. And then approximately e squared is going to come out at step 2000. Approximately e cubed is going to come out at step 3000. And I'm only going by thousands because I started with this, right? T equals 1 over 1,000. So this is the value. This is the quantization of time with respect to unity here, if you like. So it's pretty amazing. What this tells us is that this system here, right, that we solved to come up with the population of proteins in continuous time, is somehow equivalent to the Fibonacci sequence right here, which we executed to come up with the population of rabbits in discrete time. Of course, I guess we're discretizing time so that the Fibonacci sequence works out. So, I mean, what is the life of a rabbit really, right? I mean, how does a rabbit parse time? Oh, boy. Well, I'm trying to keep these videos short, so I guess I should stop unless I have something. Oh, this is where we left off. So, sorry about that. See, I left off saying that this binary sequence here can encode, as long as we have a coin toss and we're tossing coins and we're doing the random walk, this can encode the motion of a mass in 3 dimensions. And the good reason to believe this is that in information theory, the very atom of information is defined as an object that has a 50% chance of being a 1 and a 50% chance of being a 0. If we compare this with a unary system, right? The unary system is this would be a 3, this would be a 5, and this would be a 2. So the unary system requires spaces. So the unary system requires the medium to transmit information. In the binary system, we can have artificial punctuation. I mean, I don't want to call it artificial punctuation, but the binary system is self-punctuating in a sense. If we use the Zeckendorf theorem, the binary system becomes self-punctuating. The Zeckendorf theorem is that all integers can be written in terms of something called the Zeckendorf representation, which is pretty much the Fibonacci sequence. I don't know if you're interested in this. I did a whole video. I believe it's called 7 or 3.5 or something. There's a picture of Pinky and the brain there. Uh, but I really want to wrap this up because I mean the big takeaway here from quantum mechanics that I get is that this is what we're being taught, right? One over length for the well, okay, let's just think about the Schrodinger equation for a little bit. The Schrodinger equation solves the hydrogen atom, and it does so in a beautiful way because it relates the eigenvalues to the energy levels of the hydrogen atom or something like that, and the end result is that we learn that we can solve the Schrodinger equation to obtain energy levels. I guess that's clever, but if we want to ask like more detailed questions, I mean, do we have the Planck lengths uh, to measure the wave inside that little Planck length, and build a cellular automaton to simulate the wave? Because if you think of the way we simulate waves in a computer, writing computer code, the code that solves the wave equation is practically identical to a cellular automaton. Um, why can't we do that for Planck lengths? And I don't know yet, but I suspect that we're being taught this for the complex conjugated dimension of the wave function, and I suspect that this is wrong. I suspect that we should be taught this force per energy. Newtons per Newton meters. So I think we should be taught newtons per Newton meters instead of meters. Did I say that right? Newtons per Newton meters? Yeah, instead of meters. Thanks for watching, and see you next time.